All right, I'm John Hershey, if you don't know me already, and I am very, very happy to introduce Arsha Nagrani. I'm very lucky to have her working at the same place that I do in Google Cambridge, you can read her bio. She's really, when she graduated from her PhD in 2000, where she studied with Andrew Zisserman, she was already a rising star and known as such. She started so many new things. Vox Celeb is her work, and many other new initiatives and data collections that became sort of the bedrock of sort of audiovisual and other new tasks in machine perception. So very happy to introduce her. She would have liked to have been here, but for reasons beyond anyone's control, she's giving her talk from India. And okay, without further ado, Arsha, take it away.
Thank you so much for such a kind introduction, and thank you so much for inviting me to this workshop. I really wish I could be there. I think I'm the only person who's not going to be in person, but nevertheless, happy to share some of the work we've been working on in the last few years. And this is going to be work that's been done by me, but also lots of other people at Google and our external collaborators as well, and their names will be on the slides as we go along. And I just wanted to say that I actually started off in computer vision during my PhD, and then over time I've moved into doing more speech and sound, and now I'm a research scientist at Google and really working with multiple different modalities. Okay, so let's dive straight in. So before we go into audio or vision or anything, if we just take a step back from the machine learning and AI field in general, it seems like so many tasks are now just solved. So automatic speech recognition, ASR, we have these amazing models in computer vision for object recognition, semantic segmentation. In the NLP field, we now have models that can really fool people into thinking that they're conversing just like other humans. And a few years ago, many of these tasks weren't even possible. So it seems like we're at this really amazing time when everything is just starting to work. And the biggest area where we're seeing this massive boom is actually in LLMs. And this is a very crowded slide, but you guys probably know a lot of these names. Large language models are just exploding, and they're getting bigger and bigger. And it seems like every lab, every company, every university just wants to train their own language model. And audio and video models just aren't keeping up in terms of size. And some of these are just out of control. So it's rumored, we don't know, but GPT-4 is rumored to be 1.8 trillion parameters if you include all the ensembles of different models. And this is an insane size. If we look at the human brain, it has 86 billion parameters and obviously a lot more connections, but the human brain can do so much more than language. Whereas, these models are predominantly just text NLP models. So what's going on? It's not just the size of these models that's growing. There's also hype, which is growing everywhere. And, that they have great performance generalization, reasoning capabilities. But people are saying that, okay, AGI is solved, intelligence is solved, this is magic. It's like a new operating system. The world has changed. And we really now just have foundation models. And when hype grows, we all know that archive will obviously follow. And so this is a really nice summary that I like, which just shows that after 2023, this year when ChatGPT was released, just the number of papers that mention large language models, LLMs, has just absolutely skyrocketed. And okay, so this is a speech and audio workshop. Why am I talking about LLMs? So how is this affecting those of us who don't work in NLP or who work in other areas? And it turns out that we're getting really affected too. So a lot of audiovisual papers are now really using LLMs. We're using them to create data sets. We're moving from class labels to more free-form language supervision, which we're getting from these large models. We're using LLMs to control and to plan how we use various different APIs. So we might have modality-specific APIs that can do things like object recognition or sound recognition, but we're using an LLM to basically plan how we use these APIs. And we're also allowing LLMs to really affect how we model. So we're using them directly in multimodal models for things like video captioning, audio captioning. We're also using LLMs as an inspiration for architecture design, and maybe even using the weights directly. And this, I mean, there are many advantages to using LLMs. We can reuse all the existing knowledge and effort that's gone into training these big models. Many of them are open source and available. And it's also kind of nice to connect perception and language. So video, audio, this is how we perceive the world. Language is how we communicate. So it's nice to connect the two. And obviously LLMs allow us this open set generalization. So the question is, okay, great. Should we really just be taking these big language models? Is all the foundational work done? And then we just have to, project a few visual tokens, a few audio tokens. Is that what we need? And I'm going to argue that that's not what we need. And this is actually a really nice image that I like from Andrew Owens. And basically, are we building these foundation models on really shaky foundations? And we know that there are downfalls of these LLMs. They hallucinate, they have limited context window size, they can be biased. And so the question is, are they actually foundational? And if they are, then why do we have a new GPT, updated? Why are we constantly trying to align them to say different things or not say the things that they're saying? And also, if we just look at humans, humans know a lot about the world even before they speak. And they're obviously learning and building some foundation. And then the final question is also, is embodiment essential? Should a foundational model actually be able to move in the real world and understand the real world? And so I just want to kind of take a step back and look at like an actual intelligent being that we know and we have, which is us, and see how we, how do we learn and how do we reason? And we actually perceive the world with so many different sensory systems, right? We have vision, we have audio, we have touch, we have smell. And there's lots of great studies in neurobiology and psychology on why we evolved to be this way. And one of the big theories is that it gives us degeneracy or redundancy, which means that even if one system, one component doesn't work, we can still function. And a great way to study this is actually in blind people or the visually impaired, where they actually have great spatial awareness. And they do this by using touch or audio echolocation, and then they can learn about the world without vision. The other very compelling theory is that different sensory systems can also educate each other. So children spend hours just gazing at things, at objects, touching, feeling, playing with things. Like this baby is about to put this in her mouth and, taste it. And the theory is that we actually use these different senses, which are time locked and correlated to learn about properties, and this is just self-supervision, right? So this is something that we do constantly, or cross-modal supervision from different modalities. And a really nice study on this is actually on transparency. So if you have a transparent box, 8-month-old infants actually struggle to retrieve objects that are hidden in these boxes unless they're allowed to play with them first. And if they can play with them, then they can touch, then they can actually learn the visual concept of transparency really well. And transparency is a very difficult thing to learn. We know this because birds will fly into windows, and dogs will sometimes crash into windows too. So transparency is a very difficult visual concept. And yet, once we can touch, we actually get very good at learning this. So this is an example of one modality, touch, teaching another one, vision. And then finally, if we can fuse multiple senses, then this helps us with robustness. And so, we can maybe come to a better conclusion than if we had one sense alone. And a great example of this is what we see affects what we hear, and what we hear affects what we see. And the McGurk effect, which you can look up, is basically how we hear different sounds when we see different lips moving, basically, is like the basic concept. And so robustness is another great reason. Okay, so the main thing that I guess the point of this talk is to say that we really need multiple modalities as input. And if we want to build truly foundational models or really intelligent models, then they should be based on things like vision and sound and motion and sensor supervision, and not just take an LLM and try and add things to it. So that's the key idea. And this is also a very practical way, I think, to look at research, because from a practical perspective, we train on data from the internet usually, and it's inherently multimodal. So we'll have captions, text, videos have titles, description, they have audio, they have speech. So why should we be, limiting ourselves to only one modality? Why should we only be working in vision or only be working in sound? And then obviously self-supervision, getting label data is difficult. So if we can use this redundancy, we can learn with fewer labels. And finally, many applications that we care about in the field of machine learning are just inherently multimodal. So video captioning, you have video input, you have text output, ASR, audio, text, sound source localization, you have audio and vision. So we really should always be thinking about multiple modalities. Okay, so an overview. So that was just an introduction. Why I think audiovisual learning is important, both from a human perspective and also from a practical perspective. And now I'm going to dive into some audiovisual models. I've kind of structured this into 3 different parts. So first, what kind of architectures should we be looking at? And then secondly, once we have these architectures, what kind of data do we need and how do we get more and more data? And then finally, just some nice fusion applications. There are a couple. We'll see how much time we have to go through those. Okay. Is everything okay, John? I see you've come to the front.
My phone doesn't make any noises.
Okay. Everything good?
Yeah.
Okay. Okay, great. So let's dive into the right architectures then. So what is the right architecture for a multimodal fusion model? So we want a model that can basically take in different modalities, so audio, vision, text, and these different modalities have all kinds of their own properties. Some can be missing, some can be occluded. They can have various different input representations and sizes. And we really want one model that will be robust to all these things, that will be efficient and scalable, so we can add new modalities as we have them, and can also take up variable sizes. And if we look at history on different areas, we've for a long time we've had these specialized architectures for each modality. So we've had LSTMs designed for sequences, used for text and audio. And then for a long time, the computer vision field was really dominated by CNNs because they were better able to capture spatial properties, they had translation invariants. And so, there was kind of this gap, and different communities functioned very differently. And it kind of made sense because, the inputs are very different. Images look very different to, images are 2D, audio is a 1D waveform. You have occlusion in images, and audio you have noise is always additive. Then you have obviously video, which adds another time dimension. And text is, this really sparse, tokenized kind of, modality. And so we had these specialized architectures. We had different communities, different data sets, different eval benchmarks. And so when you wanted to do something like modality fusion, or you wanted a multimodal model, the dominant paradigm was always that you'd have these different encoders. So you'd always have the best image model, the best audio model, the best text model. You get some scores or outputs, and then you'd fuse them right at the end. And then you'd do your task, whatever your task is, whether it's classification or captioning or localization or anything. But this is really not how humans perceive. So the human perceptual system, there's a lot of evidence and some theories that multimodal fusion in humans actually happens very early on. And, we're already fusing audio signals with vision signals before we're actually making conclusions or before we're reaching this final classifier stage. Okay, but then suddenly everything changed, right? Because we got these transformers introduced for NLP, These were also designed for sequences, for long text sequences, but they're really great at modeling long context, and that's because in a transformer, every token can have access to all the other tokens in the sequence. Very easy to to parallelize these models because of the self-attention function, and so they were also shown to just perform excellently at scale. And when they did well for NLP, other communities actually also jumped onto this. So all that a transformer needs as input is a sequence of tokens. And images can be converted into a sequence of tokens by dividing them into patches and converting each patch into one token. You then get a long sequence of tokens. And for audio as well, you can do the same because you can take convert an audio waveform into a spectrogram. Now it's kind of like an image. And then you can get these patches and you can project them and you can get tokens. And so really we started seeing transformers being used for different modalities. And that's because any modality can be tokenized, right? And that's all you need is to feed in a sequence of tokens. Okay, so they've had great success on different individual modalities. This state of the art now for videos, audio, images, text. And then some people said, okay, maybe they're like universal perceptual models. So our goal was really, okay, can we have a single transformer model that just takes in whatever modality you have, and it fuses it early on. So it's not something that, treats these modalities very differently. And so this was work that we did a while ago at Neurips. And I mean, the simplest thing to do is we can just take a vanilla transformer. We can operate on a sequence of tokens. So we can just tokenize RGB frame and spectrogram patches, feed them all in to a transformer, and have just pairwise self-attention between all the tokens. And great, this is like super early fusion. We haven't designed anything. This actually works fine for many audio-visual tasks. But the question is it scalable? And it's actually really expensive. So self-attention scales quadratically with sequence length, and video is extremely high dimensional, and also like audio and video spaces are very dense and have a lot of redundancy. And so this was very inefficient. So we kind of introduced two very simple ideas to make this into a more efficient model. The first thing we did was we just introduced a small number of bottleneck tokens, and these are kind of just like a CLS token. So these are learnable tokens. You just add them to the input. And what we did was we allowed full pairwise self-attention within a modality, but we didn't allow it across. So there was a tension between the visual tokens and the bottleneck tokens, and a tension between the audio tokens and the bottleneck tokens, but not audio and video directly. And so in this way, all multimodal or cross-modal interactions had to be compressed through this bottleneck. And then the second thing that we did was we actually restricted this information only to later layers of the model. So we realized that you don't actually need these bottleneck layers at every single layer of, say you have a 12-layer transformer. And the layer at which you introduce these interactions, we called it the fusion layer. And this can allow the earlier layers to really specialize to unimodal patterns and then do the fusing midway through. And so this is kind of like mid-fusion. So it's not early, it's not really late. And that was it. These were the two key ideas. And we found that on most data sets and most tasks, mid-fusion actually outperforms both early and late. So on the left plot, we have performance on the y-axis and the fusion layer on the x. And for this particular data set, we found that about 8, fusion layer 8 is when we had the highest performance, but it's roughly always around there, 6 or 8. And then on the right, we have efficiency on the y-axis in the form of flops, and the fusion layer on the x-axis. And we found that our bottleneck model, which we call MBT, was actually just far more efficient, no matter what fusion layer. And that's just because the bottleneck tokens are actually tiny compared to all the tokens in the sequence. So we found that we could do really well with just 4 bottleneck tokens. Great. So then we applied our model to different video tasks for action recognition. We also applied our model to sound event classification, tasks like audio set, VGG sound, kinetic sounds. And we found that this model got state-of-the-art results, but was much cheaper than just like an early fusion transformer model. And the nice thing about this is that our framework is general. And so it can be used for any modality that can be tokenized. And as we know, anything can be tokenized because you can just divide an image into patches, or you can divide, audio as well, and then convert it into these 1D tokens. The framework is also general and can be used with any number of modalities. So we've added optical flow, and these are updates that we've actually done internally. So internally at Google, we've used this model with text, pre-extracted embeddings, flow, various different kinds of modalities, and it works efficiently. And if we just want to maybe look at some of the attention heat maps, so this is kind of a nice thing to look at. These are there's one frame from the middle frame of a video from audio set, and then I have the label there, so like baby cry, piano music. And then we look at where vanilla fusion model, this would be without our bottlenecks, would focus, and then MBT, which is our bottleneck model. And we actually found that the bottleneck model was actually focusing more on sound source regions. So baby cry, it's like more on the mouth, it's less distributed, it's more focused. For the piano music, it's like more on the fingertips. For objects that are already well localized, I mean, the bird, it didn't make much of a difference. But it just felt like the attention was looking at specific regions, more kind of condensed, compact regions. And that's because we think that it just has fewer, it has fewer connections because it's just forced to use these bottlenecks. Okay, so to conclude this section, essentially transformers are good. They're used for all modalities. This means they're pretty good for multimodal fusion architectures, but we know that self-attention doesn't scale well. It's quadratic. Audio and visual spaces are highly dimensional. And so I think key research in the modeling space in the future will be on efficiency. It's also not clear that we've solved how to tokenize these dense spaces very well. So for audio and visual, for language, we have the tokenization problem solved. And we can do, these huge, large language models. But I think for audio and video, it's still like an open problem. And so it's still an exciting area to be in. Okay, great. So now that we feel like we have some architectures, how about data and data sets? And so in this section, I'll kind of focus more on how we can use cross-modal learning for data. So how we can use different modalities to get us labels that are maybe hard to get otherwise. And I'll do it with a specific task. So the task in question is actually video audio captioning or video audio retrieval. And this captioning is basically given an audio or video, we want to generate a sentence, and retrieval is given a text query, which can be any free-form query. We want to be able to retrieve a matching audio video from a data set. And the reason why I think this is a really nice task, good task to study in general, beyond obviously being useful, is that natural language descriptions can be as detailed or as coarse as we like, so there's no fixed label space. And then also from an AI perspective, I think I mentioned this already, it's kind of nice to be able to bridge this gap between how we humans perceive and how we communicate. And so if we can have models that can do these tasks really well, then they're actually trying to solve this fundamental intelligence problem. Okay, but how do we get good data? So I think anyone who works in this field is just struggling to get really nice labeled audio and video data. So there's two things we can manually label. So we have these video text data sets that, manually labeled, like spoken moments in time, WebVid. They're all great, but they're not very big. And audio text, similarly, we have audio caps, Clotho, there's a bunch, Max. But again, they're not huge, right? We're not talking about billions and millions scale. And then if we look at semi-automatic methods, there are some ways we can get this data automatically from the web. So we can scrape, YouTube titles, descriptions, maybe Instagram hashtags. But for video and audio, we really require lots of samples because this data is so weak. The text is not really a caption. And video and audio are dense spaces. So we don't really know which part of the video, which part of the audio is the text describing. And it's expensive to verify. Images, on the other hand, images are a lot easier. So for example, conceptual captions, these data sets are huge and they're much cleaner. And so the point really is, can we somehow use multiple modalities? In this case, can we use images as like a bridge? Okay, so what we have is we have a lot of static images that are paired with language captions. And this is because of alt text on the web. So we have data sets like conceptual captions. Internally, we have Weebly, OpenAI. Many companies have their own versions of this where they've scraped the internet and they've got images and they've got some text. And images are cheaper to annotate, right, or verify. And so you can do some cleanups. You can have a fairly large data set. Okay, but what we want is we actually want audio and video data that's paired with these language captions. And what we have is just the images paired with captions. So this was work that was at ECCV last year. And what we did was we basically transferred supervision from images to video or audio. And we did this by starting with the seed image captioning data set. So take anyone like conceptual captions 3 million, which is public. We then went to video frames online. We tried to match the seed image to frames. And if we found a match, so like say this pop artist, we went and looked for other looked for frames and videos that matched visually using a similarity model. And then we just extracted short video clips around the matching frames, and we would just transfer the caption. So in this case, we have a short video clip with audio, and we've just transferred the caption from the image captioning dataset. And here are some examples. So on the left is from the captioning data set, the seed image and the caption. And then on the right, we have videos that we mined. And for the top row, you can see, for the same caption, we get these different kind of angles. These are videos, by the way. I should have put GIFs, but these are videos. And for this statue, we have this different type of camera motion. For the throwing the pitch, there is some audio associated with these videos. And obviously, this is weak supervision. So the caption doesn't match every mined video perfectly, but there is some correlation. And here are some more examples. So a black bear in a forest. We got lots of videos of black bears. I like this palm tree thing because it's actually an animated image, and we found good videos in this video. Actually, the right one, the coconut actually like folds down and breaks, and there's some sound. And then some more examples. So this actually gives us this data set. We called it Video CC 3 million. This we've actually publicly released outside of Google, but you can also just scale this up with whatever image text data set you have, and weekly mine this kind of video and audio data that's paired with text. So some results, we find that actually training on Video CC gives us really great results for video retrieval and video captioning. So these, the numbers are not meaningful, but this is just on the MSR VGT 1K evaluation set. We also got some good results of video captioning. So How 200 million is a large data set with supervision from ASR, from the speech, and models that are trained on that don't really generalize well for video captioning because they follow the style of speech. So you can see there are some examples here in red, which aren't really great captions for these videos, but our model trained on Video CC is actually pretty decent in a zero shot manner. And then this is kind of, I think, the nicest result that we got. We actually got good results for audio retrieval as well, outperforming all state-of-the-art papers that train on audio caps and Clotho. And all we do is train on these weekly mined videos. So we have like this baby on a white blanket. This isn't captioned from an image, but we found this video with the baby. We found videos of, streams. And training on this weak data actually gave us pretty good results for audio-only retrieval. And so I think there's a lot more to explore in the space of getting weak supervision for audio to do retrieval and captioning. Okay, so that was one idea. The other idea for weak supervision, which is used really widely in the community and is a great idea for video retrieval and captioning, is to just use the speech that comes for free with videos. So we have all these videos online, and many times the speech is actually very strongly correlated with the vision. So you can see this like cooking video and this Thai. If we can transcribe this speech to text, which we can do because we have such great ASR models now, then we actually get a lot of great weak supervision for vision models. And so with this, there's all kinds of videos on YouTube. There's instructional videos, vlogs, product placements, ads. Many of them, the speech is actually very relevant. And so I'm not going to go into too much detail. We have a number of papers on this. This one, Vit2Seek, is a video captioning model that was just at CVPR this year and is also open sourced. And in this model, we actually take in speech and input frames and we produce a caption. And the nice thing about this model, again, details are in the paper, but the nice thing is that we actually produce dense captions. So at the bottom, we have a woman runs with a javelin, then she throws it onto the field, then she throws a second javelin. So these captions are actually referring to previous captions. And then she waves to the crowd and holds up a flag. And the nice thing is that these captions are trained just from speech. So we train it on the YT temporal 1 billion data set, which is just transcribed speech and vision. And so we can get some good results without a huge manually labeled set. Okay, how much time do I have? Don't know when we start. Okay, I think I have a little bit. Great. So that was data, and I think what's really nice is that if we look beyond, so if we work in speech, if we look beyond, look at vision, we can really get good supervision from using these other modalities, and that's actually how we created VoxCeleb. So VoxCeleb is a speaker recognition data set, which has now done 5 years of challenges. And when we created it, we actually used face recognition to create the VoxCeleb data set. And so that was also another way that we kind of used, we used vision as a cross-modal source of supervision to get data for speech and speaker recognition. Okay. Great. So that was a lot of stuff. Now I kind of just want to go into some nice fusion applications. So this is my favorite audio-visual application that we worked on at Google recently, and I'll just briefly cover two papers. So there was InterSpeech last year, and then a CVPR paper this year. And our goal is really ASR. So ASR is it solved? So it's really good. But there are cases when ASR fails, obviously, and there are challenging cases. And this is when you have many different types of accents that are not seen in training, background noise, different types of pronunciations. And in these cases, we argue that you can actually use vision to make your model more robust. So I'm going to try and play this video. Let's hope it plays.
The thumb reaches for the coin.
Okay, did everyone hear that? So basically, if we take an audio-only ASR model, it says thumb reaches for the con, C-O-N. But once we add in an audio-visual model, it's very obvious that this is the coin, right? You can see it in his hand. And so these are cases where really vision it's a no-brainer to use vision. And vision has been studied for ASR, but it's mostly only been studied for lip motion. And that's an obvious cue to help when people are speaking. But, you can have cases when speakers are far away in a video. You can have egocentric viewpoints. Recently, you have videos of people wearing face masks. So we actually were more interested in seeing how vision can help with other things like objects and actions and so on. And so what we have is we actually propose this avatar model. It's a very simple model. It's an end-to-end transformer with early fusion. The model we actually use is MBT, which I introduced earlier in the talk. It takes in visual in image patches and spectrogram patches, and then it has a decoder that just produces text. We also found that if we just train this without, doing anything special, then the audio stream will dominate because ASR is an audio-dominated task. So we actually did a very simple thing where we just mask out random parts of the audio, and then the model actually was forced to look at the vision and to create an actual multimodal model. And then we evaluated this with both artificial and real noise. And so artificial noise is very easy to add a test time for the task of ASR. So you can randomly mask out some of the signal, or you can actually add in noise from different classes. So we use the audio set noise category, and we just added in some noise. And what we found is that as the noise increases, our models, the robustness, the importance of vision helped, and the masking strategies also during training improved performance. But you can't submit a paper with just artificial noise. Reviewers are never going to accept it. So we also tested our model with real noise. So we create a new test set for ASR called Viz Speech. And the way we do this is we select challenging examples from YouTube where audio only ASR fails. So we used a bunch of models, but don't worry, it's not a model only created data set. We also manually checked it. We manually verified that these were kind of tricky cases, and then we corrected the transcript. And this is available to download online. And we found that, again, the same conclusion. So vision helps in all the cases, no matter different levels of the noise. And again, the masking strategies that I mentioned earlier help to improve performance. And I'll just play some videos. So when I play the video, you can see the A is audio only, and then A plus V is the audio plus visual performance.
This is a glow big plant. It's a small one.
Okay, so audio only said it's a glow big plant, but vision corrects it to globe eggplant. So that's a kind of tricky concept, I guess, to get from audio alone. Let me play this full screen. Okay, this video is not going to play.
This is a glow.
That's sad, but I have more examples later on. So, okay. Great, so that was good. Avatar was a good model. But then as follow-up work, we kind of thought that, is Avatar really reinventing some parts of the wheel? So we're training these ASR models from scratch, from audio and visual spaces, using this MBT model. And we found that if we train on these web videos, it doesn't actually generalize to new domains without training. And also, the audio field has just spent so much time building state-of-the-art ASR models that we're not utilizing all that knowledge and information that has gone there. And so we proposed this new model called AV Forma. This was at CVPR this year. And basically, the basic idea was that there are these strong ASR models, such as BestRQ, and now I'm sure there are even better ones, that are just huge. They're trained with self-supervision in the audio domain. They have this great generalization performance. And then we also have really strong vision models like CLIP that also generalize well. So why are we training this model from scratch when our goal is really just audiovisual ASR? And so what we decided was, can we reuse this amazing speech model and reuse this vision model? And we do this in a very lightweight way. So we take the BestRQ speech model and we just inject vision into it. And we do this actually using two types of adapters. So we take frozen clip features, we project them, so that's number 2 over here, visual projection layers, through a simple linear layer. We feed it into this big speech model that's already trained, and then we add in these bottleneck layers in the encoder block, which are basically just a few layers interleaved in the model that are trained. Everything else is frozen. And we train these separately. So we have a curriculum strategy. So first we train one, which is the bottleneck layers, and then we train the visual projection layers. And we found this was important for good performance. And now we find that for audiovisual ASR, we can actually get good zero-shot performance across domains. So earlier we only really evaluated on web video, but now we evaluated on Ego 4D, which is an ego-centric data set. And we also did well on traditional ASR benchmarks, so things like Libri speech. And this was important for us because, if you have a new model and it does well on audiovisual, but then you go back to the traditional ASR benchmarks are doing badly, then, that's bad. So that was the basic idea. And now I'm going to try and play all these videos. Okay.
Slide the carrot pieces into thin strips lengthwise.
Same method, pour the egg yolk into a bowl.
So the audio only says bowl, and then with the vision, it corrects it to bowl. And then It's always the last video on the slide that doesn't play. No. Okay, that's fine. I will describe the video to you. So it's basically a popcorn video, and he says kernels, popcorn kernels, and the audio only model says a different type of kernel. So this is kind of nice, you know, with the vision, it can really correct these homophones, which from the audio stream only, it's hard to get. Obviously context should be able to help, but yeah, popcorn wasn't actually in the ASR. So we can see how many kernels were left behind, and the audio only model uses this different type of kernel. Okay, and I have some more. Let's see, this is a nice one. No. Okay, well, there's lots of examples on our website. I don't think these videos are gonna play. But you can kind of see, so this is, it's like a car that's driving, and the audio is just, you can't understand it. It's like the ASR audio only model is like Muhammad, something completely and unrelated, and the ground truth is drive over it. And this is nice because it's a completely different domain and it's egocentric perspective, and our model corrects it with vision. An object here from clove is corrected to loaf. So here you can see that the ground truth is I'm using a garlic loaf to make the sandwich. But you know, if you just use context, clove seems more reasonable than loaf, but there's actually a loaf of bread. So the vision helps to correct that. And then this one, this is just a tricky background noise example. But there's lots of examples on our website where we show that vision can really help with this task. Okay. And then, okay, I'm reaching the end, but just some more nice examples. So I really think the egocentric viewpoint is a really great place to study audio-visual fusion. And that's because audio is very useful in the first-person domain because the microphone is close to the person. It can record sounds that are outside the view of the camera. And so, you know, it's just nice to have these different signals. I think Ego 4D now has a bunch of other modalities added as well. And you know, the difference between these different actions like washing steak or frying steak, you can really hear on the sound. So it's kind of nice to study the vision and the audio together. This was another nice piece of work that we did with Oxford, with AZ, and the anthropology department, and it was actually recognizing chimpanzee behaviors in the wild. So this is nice because with animal research, you know, you don't have privacy. Well, you don't have the same privacy issues. And also it's very useful for conservation, which is nice. And so we were doing action recognition for chimpanzees, and we found that actually audio is what really helped us in the end, because these actions like nut cracking, drumming have very distinct sounds, but it's very hard to see in this camera trap style footage. Another great piece of work that I like is this area of movie audio description. So this is for the blind or visually impaired people, where you basically describe what's happening in a movie. And I think all movies now have a requirement to produce an 80 track as well. And so we were trying to create this 80 track automatically. And this is very different from video captioning, just general video captioning, because you need these dense descriptions. It has to be complementary to the audio, so you don't repeat what's in speech. And it really should aim at storytelling. So I'll play an example of 80. Okay, let's give it a second because it's a cool video. Okay.
A man approaches toying with a lighter. She turns her head and finds Jack standing beside her.
I buy you a drink?
Yeah, I'd love one. Sit down.
Okay, so you get the idea. So basically it's like this description. And for this task, multimodal features are very important. So, you know, speech, visual features, previous AD, character names. And here are some examples of our model automatically producing AD. So these are two movies. These examples don't show what's happening in the speech, but if you look at the reference, we have examples online of movies where you really need to pay attention to the speech, to the vision, to the previous context, and then generate these type of captions. Okay, so great. I think we still have time for questions, but just to conclude, I think that LLMs are exploding and they're great, but for a truly foundational model, it feels like we need to really learn from audio and visual spaces, and just as many modalities as we can. And then we went through some ideas on architectures, data, some applications of fusion. So, I really think that, given we live in this multimodal world, we really need models that can understand video. Transformers are great. They can operate on any input that can be tokenized, but they are expensive, and so we need to find a way to make them more efficient. And there's so many practical applications with audio and vision. Audio can help for video retrieval, while vision can be important cue for audio tasks such as ASR. And I think that once we really have these multimodal models that understand video, then we can say all this hype is worth it, and it's magic, and we've solved AI and so on. But yeah, that's everything for me. Questions?
Let's first thank Arsha for a wonderful talk. So we have some people with microphones who can bring them around. If you have a question, raise your hand and maybe, yeah.
Hi, Arsha. Thank you so much for the talk. That was excellent. I use transformers in my own work, and your bottleneck tokens for fusion are just brilliant. I love that so much. But my question, I saw you had 2 CLS tokens there. What was the actual training objective that was using 2 CLS tokens?
Yeah, that's a great question. So we had 1 CLS for audio, 1 for video, and then we were training with classification. So now we've trained MBT, like I showed, with the decoder for ASR, and we've trained it for captioning and so on. But the original MBT paper was trained for classification, and it was trained for action recognition or on audio set. And we actually found that having 2 CLS tokens and averaging the 2 tokens and then feeding it to the softmax did better than having just 1. It's probably just easier to pull out the information from each modality. But we also tried just feeding in the bottleneck tokens to the softmax, because it should, if it's pulling everything, it should be able to. But this just worked out the best, to have 2 CLS and average them.
Very interesting, thanks.
Any other questions? Yes, Gael.
Yes. Thank you very much for your talk. Very interesting talk. I have one question regarding the necessity to retrain everything when you move from one modality to multiple modalities. And you said that, well, audio, if we look at the spectrogram, is kind of an image, which is not wrong. But then, can't you do a pure visual model and make it work for multimodal just by saying that part of the image that you tokenize are spectrograms?
Yeah, it's a great question. So I think, it's a good question. Spectrograms are images, but they're very different, right? So instead of, X and Y, now we have frequency on one axis, time on the other axis. In an image, each object pixel is opaque. So if you have 2 objects, they'll never share a pixel. You have occlusion, whereas in sound, like the spectrogram, 1 pixel in a spectrogram can represent different sound objects just because it's additive. So I think the statistics of spectrograms are very different. But having said that, the MBT model does exactly what you said. It tokenizes images, it tokenizes spectrograms, it feeds them the same model, and it lets the model figure it out. And so, it's a good question. And I don't think you have to retrain models. That's what we did with AV Former, right? We took this big speech model and we just injected vision into it. I don't think you necessarily have to retrain every time. But I think when we think about foundation models, we should start off with the place of, okay, how many modalities can we use, as opposed to, take an LLM and just add something to it. But no, it's a great question.
Thank you.
Okay, maybe we have time for one short question. Is it, okay, and then we'll move on to the next week.
Thank you for the presentation. And this is probably related to the last question, and also I don't expect anyone to know answer to this question, but again, like using spectrogram is like, I think there is a fundamental problem using spectrogram as because it is an image, right? And audio is not an image, right? So, and you said there was convolutional layers used for image and RNNs, and then now we have transformers, but we still use spectrograms. I mean, have you ever thought about maybe some other layers, some different kind of layers for audio? Not CNN, not spectrogram, something direct, something, I don't know. I'm just theorizing here.
Yeah, I think it's a great question. You're right. Spectrograms are not ideal. We should be learning from the waveform directly. It's a 1D. It's just a very long input. But, spectrograms, we also throw away the phase. It's just a magnitude, though. Theoretically, you can recover it. So I haven't personally tried. I've trained a few transformers on 1D waveforms, and they've not done as well as spectrograms. But I think some more audio experts probably in the audience will be able to answer that better.
Thanks very much. Let's thank Arsha again.
Great, thanks for having me.